Traditional charging systems have existed for as long as vehicles have had batteries, and they operate only when the engine is running. Originally, all vehicle charging systems had a DC generator at their core, but as the electrical load on the battery grew, charging systems had an upgrade to an AC generator. These older AC generators use an internal or external regulator to control the alternator's output voltage range of between 13.8 and 14.2 volts. Modern ECM controlled charging systems have taken a different approach. Let's take a look and compare the two systems. This is a typical older style charging system. We can see the battery, alternator with internal regulator, fused ignition supply, ground points, and the charge warning lamp. With the key in the run position, ignition voltage is supplied through a fuse to the alternator field terminal on the voltage regulator. Ignition voltage is supplied to one side of the warning lamp with its ground circuit traced through the L terminal and regulator. When the engine is started and running, the magnetic flux created by the field winding rotates and cuts through the stator winding. Current is induced through the stator windings. The current is rectified and then exits through the B positive terminal. The regulator senses the output voltage at this terminal and then adjusts the field winding magnetic flux, regulating the alternator's output. The regulator applies current to the L terminal and warning lamp. With positive voltage on both sides of the globe, it turns off. This is an ECM controlled charging system circuit. It's very similar to the older style, but with the addition of a field winding control circuit, a current sensor, engine control, and body control modules. This system uses a software program within the BCM and ECM to determine how much current the alternator will supply to the vehicle's battery. There are several charge modes to choose from, and each is specific to different operating conditions. Let's take a closer look at this system and its operation. When the key is turned to the start position, there is high current flow to the starter motor. The BCM is able to monitor the amount and direction via the battery current sensor. With the engine running and the idle speed stabilised, the BCM uses the ambient air temperature, battery voltage, and electrical system load to determine which charging mode is required to return the battery to its optimal level. When the BCM has detected which mode is required, a corresponding command is sent to the ECM via the high-speed communication bus. The high-side driver within the ECM is operated at a duty cycle that is relative to the charging mode selected by the BCM. This control is then sent to the alternator's L terminal. The alternators used in ECM-controlled charging systems are similar in construction and operation to conventional types, although they have a major difference. The voltage regulator has been substituted with a field winding control module. The module amplifies the signal and adjusts the strength of the rotor's field coil so that the alternator's output voltage corresponds with the selected charge mode. The ECM receives feedback via a PWM signal generated at the alternator's F terminal. This signal is used to monitor the field control module for faults. When the BCM determines that the battery voltage is back to a normal value, a command for reduced field winding duty cycle is sent to the ECM. ECM-controlled charging systems use several different modes to effectively maintain the battery charge and manage all electrical loads. The different charging modes used by vehicle manufacturers may include battery sulfation mode, fuel economy mode, headlamp mode, startup mode, and auxiliary battery charging mode. When the BCM selects a particular charge mode, it does so based on the electrical system load, current battery voltage, ambient air temperature, vehicle drive time, and time from engine start. For each mode selected, the BCM will command the alternator field strength to a particular duty cycle for a predetermined time, so that the voltage and current requirements are met. Basically, this means we'll see different voltage outputs from the alternator at different times, and this is normal operation. Just after engine start, we may see voltage levels in the region of 16 volts. Or, if the engine has been running for an extended period of time with no excessive electrical load, we may see voltages around 12 volts only. If you find yourself in a position where you need to test or diagnose a charging fault in an ECM controlled system, you'll need to access the charging specifications and mode types for that vehicle. A key component of an ECM controlled charging system is the current sensor. The sensor is most commonly fitted to the negative cable and is able to measure all current flow to and from the battery. There's a couple of different current sensing devices found in smart charge systems. We can classify them as direct and indirect types. These sensors operate using an indirect measuring, open loop DC design, whereby a core is placed around the negative battery cable. Current flow through the cable produces a magnetic flux that is relative to the flow of electricity. The magnetic flux is then concentrated by the core and then measured by the hall generator. This signal is too low to be useful, so it's first amplified and then conditioned to become a digital output. In this instance, we can see that an output from the sensor with a 50% duty cycle would indicate no current flow to or from the battery. A duty cycle above 50% would indicate current flow towards the battery, like when the alternator is supplying current. And a duty cycle below 50% would indicate current flow away from the battery, as in a starting event. Open loop sensors normally have circuitry that allows for temperature compensation for improved accuracy of measurement. Shunt-based current sensing uses the direct method, where a shunt resistor is placed in series with the negative cable and terminal. When current flows through the circuit, a voltage is generated across the shunt resistor that is proportional to the current flow. Forward or reverse bias current flow is simply measured as a positive or negative voltage. This signal is conditioned and converted to a digital output for the BCM. When measuring output signals from the current sensor, we need to be aware that manufacturers use different methods of transmitting information. The output from this vehicle is a simple 5-volt duty cycle, which changes relative to current flow. We have attached a low amp clamp to the red channel and can see that an increase in current flow equates to a decrease in duty cycle. The output signal from this vehicle is very different. This is because its current sensor sends information to the BCM via a local interconnect network. Current flow and direction is measured by the sensor and converted to a LIN protocol. Not only is this a fast and reliable way of signal transfer, but the BCM can also use the data bus for fault monitoring of the sensor and circuit. The body control module is the brains of this operation. It stores the vehicle charging mode programs and selects each one based on inputs directly or from information sent on the vehicle's communication network. The BCM is responsible for sending charging messages and fault information to the driver through the information display. The engine control unit is tasked with receiving alternator charge requests from the BCM and then commanding the field control module to carry them out via a PWM control sent to the L terminal. We can see that the PWM duty cycle changes based on ECM commands. These commands are directly related to the charge cycle selected by the BCM. The ECM receives feedback via the F terminal at the alternator. The field control module produces a square wave pattern. The ECM monitors for a change in the duty cycle, indicating a system fault. When working around or diagnosing an ECM controlled charging system, do yourself a favour and make sure you understand how that system operates before starting. I'm Clint. Thanks for watching.